Okay, this is a tutorial for powdR version 1.2.1 and the Shiny application for it, which has changed a little bit since previous versions, so it's worth just doing another video to introduce the new functions, etc. So to load the Shiny application, first thing we need to do is load the package. And once that's loaded, we can call the function run powdR, which will load the web application in your default browser. I tend to use Firefox, which seems to be pretty good for Shiny applications. Once loaded, you'll see the application and the 6 tabs that it has in total. This video will run through the first 5 of them, and this will eventually end up in the Help tab. So to begin with then, we're going to look at how to use the reference library builder and what this is. This is essentially a way of building a reference library in a way that is compatible with all the functions in the package. You can do this via code quite easily, but this is another alternative way to do so. To create these powdRlib objects, they're called, these reference libraries, we need 2 pieces of data. We need X-ray diffraction data, and we need the information of that diffraction data. And these are supplied in 2 different CSV files. And in this video, I'm going to use some example data that can be downloaded in the red question marks. So first things first, to load the XRD data. Actually, let me just show you what this is comprised of. So this is a small library that's used as an example in the powdR package. And on loading the data, what we see is that the first column is called TTH, and that is the 2 theta axis of the X-ray diffraction data. The remaining columns, in this case 14 columns, each have a unique column title, which denotes the ID of the reference pattern. Try and avoid naming these try and avoid the inclusion of spaces and hyphens in these names, as it's not that compatible with our data frames, and also try and avoid starting the names with numbers as well. Those are the few general rules for creating these unique IDs. And each of these other columns essentially represents the count intensities of a reference pattern. So by plotting the 2 theta axis and any of these count intensities, you'll end up with a one-dimensional X-ray powder diffraction pattern. So the other piece of data that's needed to create the reference library is some phase information. Again, a pretty simple CSV file. And this contains information on all of the phases that you'll find in the reference library. So in this case, the phase ID column, the first column, exactly matches the column names from 2 through to the end. So they have to match, and they have to be the same order as well. The second column is a phase name column, which gives you the opportunity to assign mineral groups to the phases in your library. And this essentially allows you to have more than one phase, more than one pattern for a given mineral in the library, which is often quite useful. You might have several different feldspars in there, for example, which exhibit different solid solutions and therefore have slightly different diffraction data. The last column in this phases CSV file is the RIR column, which is the reference intensity ratio and is crucial for computing the quantitative estimates of the concentrations in the final output. So I've already downloaded those 2 files. and I'll just load them into the web application. And once loaded, if you click the Build Library button, it will do just that. It will build a library, and you'll get a tabulated output of what that library contains, which is just like the table we've been looking at actually. It's phase IDs, phase names, and reference intensity ratios of all the phases. By default, it'll only show you 10, but you can change that to 25 or 50. And you can also search for different phases in the library. Depending on the size, it may or may not be that useful to be doing that. So we have our reference library now in the right format for use with the powdR package. And now we're going to export it. Now, when you export it, you can give it a unique name, which will be what it's called if you were to then load it into R manually, as opposed to using this application. And you can download that as a .r data file, which is the file type that this application uses. I've already done that, so I don't need to save that. I can move on to the reference library viewer. And as the name suggests, this is just a way of visualizing your reference library, which can be useful. I'm just going to load the library that we've just created into the app. And when you load it, you should get a plot of the first diffraction pattern in your library. In this case, it's a quartz pattern. And you can add other different phases in there, any number of them really. And you can then remove them by clicking and deleting. The plots that you get are interactive plots, so you can zoom in on different areas of the graph. And you can hover over the data to get information about d-spacings, 2θ, and counts. In this case, the d-spacing is calculated based on the wavelength, and at the moment, only copper and cobalt wavelengths are accounted for. Other things you can do with the plots are to double-click on any of the legend items to isolate that item singly, and you can double-click on that again to get the others to load back. And there are various other things you can do with this JavaScript library. If you scroll down a little bit again, we've got this tabulated information about the reference library and all of the phases that you might find in it. Now we're ready to move on to the reference library editor, which is the third tab in the application. The first step in this tab is to load the library you want to edit. Again, we'll just load the example library we're working with. And the second part of the process of subsetting is to select the mode that you want to use. You can either choose keep or remove. For now, we'll stick with keep. And then the third part, the most important part of the subsetting, is actually selecting the phases. So this is just a case of selecting any phase you like. You can search for different names, which is useful if you're dealing with large libraries. So I've selected a few there, and to actually do the subsetting, just click this button, and you will get a tabulated output of your subset library. In this case, because the mode is keep, and we've selected 5 patterns, it's just selecting those 5 patterns from the library, which are tabulated here. If we change that to remove and recompute, it will remove those phases from the library, and you'll be left with whatever's remaining after that. So in this case, we have 9 phases. And as in the previous tab, you can export the library as R data file, which can then be loaded into R separately or used in this web application as well. And the main reason for this is that sometimes it's useful to have specific libraries for a specific set of samples that makes life easier and makes your fitting less prone to errors. Now we'll move on to the fourth tab, which contains the most amount of functionality in this application. And this is the full pattern summation tab. And for doing this, you'll need firstly your sample data, which must be in XY format, which is a space-separated ASCII file. You can have a look at an example here of the sandstone soil data. I'll just open it in WordPad, and you can see that it's a simple space-separated file of an X and a Y axis. And you can produce these kind of files quite easily using the powdR converter, which is specifically designed for converting file types of X-ray diffraction data, and the XY files are one of the outputs you can use, so I pretty much always use that. So I'm going to load this sandstone example into there. The other thing we need is the reference library, which so far is the object we've been working with. So I'm going to use that. So we have our sample and library loaded, which are the two pieces of data needed for the fitting process. The next thing we need to do is select the mode. There are two modes that you can use in this tab, manual and automated. I'll go through both of them, but first I'll introduce the manual mode. Full thing, you can select various different optimization routines and objective functions to minimize. I'll keep these as they are. And the fifth part of the process is to actually select the phases that you want to use in the fitting. So first thing I normally do is just to add one phase that I know will be there, which when dealing with soils is pretty much always quartz. So if I want to add quartz, there are in this case a few different options for me to do so. I can either select quartz in the phase names section here, in which case I'll select all quartz patterns in the library, or I could select them individually in the phase ID section. So clicking this button for just quartz saves me clicking twice, I guess. So I'm going to just add quartz in there, and then I need to select an internal standard that is going to be used to make sure that the peaks of the sample are aligned to the standards. So I could choose any of the patterns in the reference library, and these will be added to the fitting process. But I'm just going to stick with quartz because I know it's got pretty well-defined peaks, and it's ideal for aligning due to that. The sample that we're working with was not prepared with a known internal standard and with a known concentration, so we're just going to leave this box blank. But that's something you can add in. So I'm going to click to start the computation, which will start the fitting process. And because we've only added two reference patterns, it's very fast. Results should compute in just a few seconds. And the outputs you'll get should be in this kind of format. You'll get a table at the top and then a figure below. The table provides all the information on the reference patterns used in the fit and their concentrations. And because we haven't defined an internal standard concentration here, the fitting process assumes that the phases sum to 100%. And in that assumption, it's also important that you can account for all of the peaks in the pattern in order to get accurate results. And in order to know if you've accounted for all the peaks, you have to inspect the fit. And that's what the figure's for, really. And again, you can zoom in to the figure to have a look at the features of the fitted and measured patterns. And in this case, we can see that the measured pattern in black and the fitted pattern are pretty similar in that the quartz peaks account for the major diffraction peaks in the data. but there's a big discrepancy between the fitted and measured in terms of the background, which when dealing with soils would usually be a sign that there's some kind of amorphous phase in the data that should be accounted for. So I'm going to go back to the Select Phases tab and add organic matter, and then recompute. And again, because we haven't got many phases contributing to the computation, it's relatively quick. And now if we zoom in on the data, we see that adding organic matter has actually almost entirely accounted for that discrepancy in background that we were seeing, with the red and the black lines now almost overlapping. But there are other features in the data that aren't accounted for, this 7 angstrom peak here and this broad shoulder to one of the quartz peaks here. Minor features, but important features nonetheless. And there are various other pieces of software for identifying what these peaks might be, but in powdR there's an approach for automating this selection process using the reference library. So if you have a large reference library that's likely to account for any mineral you might come across, you can use this automated approach on your samples. So we're just going to switch to automated mode up here. And the automated mode allows you to just throw everything in your library, if you like, to the fitting process. So I'm just going to do that. I'm going to keep the internal standard as quartz, and I'm going to recompute the results. And because we've added a few more phases to the fit, it might be a little slower. So to just check the progress of things, you can go back to your RStudio console and see these text messages, I guess. And once it reaches a completion message, you know that it's finished and the results should update. So we have the updated results here plotted in the application. We see that the automated algorithm, out of all of the phases we supplied, it's ended up only using 7 of them. And if we go down to the bottom here and inspect the fit, we can see that the 7 angstrom peak is now accounted for. It turns out to be a kaolin mineral. We can also see that these broad features that shoulder the quartz peak are also accounted for via feldspar minerals. So this automated approach has selected the appropriate phases from the library, and once you're happy with or almost happy with the results, you can save them, and there are various ways of saving them down here. First is to download the measured pattern as an XY file, and you can also download the fitted pattern as an XY file. Note that the measured pattern will be slightly different to the data that you originally uploaded, because that pattern has been aligned to match the alignment of this whatever you've selected as the standard. So by downloading them here, you account for that. The other thing you can download is a CSV file of all of the concentrations, which is essentially this table of information. And the other thing you can download is the powdR FPS object, which is the R object containing a lot more information about the fitting and all of the data to go with it. So this is the biggest bundle of data, if you like, and this is what you can download and save to come back to later, which is what we're going to move on to now. So I've already saved a similar output that I'll use in the next tab, but go ahead and save that if you're trying to follow. So the final part of this tutorial will introduce the results editor, or results viewer and editor tab. And this unsurprisingly allows you to view the results simply as tabulated and graphical forms. And alternatively, and very, very usefully sometimes, you can actually edit the results as well, because this approach to full pattern summation is quite an iterative endeavor sometimes. So it can be useful to save something and come back to it at a later date. So I'm just going to load an example of some data of a fit that I produced on the same sample we've been working on. And by loading it in, we automatically visualize the results in the same format we were looking at in the previous tab. So again, this is the sandstone soil example. Now, if we wanted to edit this output, if we weren't happy with the fit or wanted to see if we can improve it, you need to load the reference library that you were using to produce the original results, which again is the one we've been working with. There are options for selecting the optimization routine and the objective function to minimize. We'll just keep those as they are. And now when we're looking at the select phases box, we can select certain things we want to remove. So in this case, we have an option of removing any of the 6 phases used in the current outputs. Let's have a go at removing the organic matter. And then you can also select phases that are in the library but not currently in the fit. So let's have a go at adding other feldspar minerals. We'll keep the internal standard as quartz again, and again, click this button to recompute. And if it's taking a while or you're not sure what's happening, go back to the RStudio terminal, and here you'll see that it's currently optimizing the results and it's just finished. Now if we go back to the tab, the application, the results will not be any different yet because we need to actually select the new results in this drop-down box. And on loading that, we can see our updated table. We have several new feldspar minerals that have been added to the fit, and we no longer have any organic matter in the fit as well. And when we zoom in on the output, we can see that it's a pretty messy output, and this is a typical case of not accounting for the background properly, which results in lots of strange peaks being brought into the fitted pattern. So this stresses the importance of accounting for the potentially amorphous phases in your sample that can strongly account for the background if you want to get accurate results from this approach. So I'm going to recompute the results again by letting organic matter back into the fitting process and recompute, which again will take a few seconds. And because we're already in the new results tab, it should automatically update the results once the computation is finished. But again, you can go back to the R console and check. So now we have another output. We've got the organic matter back in there. We still have just one feldspar, 2 plagioclase phases in there. Looks like the albite has been retained from our addition here, but the sanidine and autoclaves have not. And that would be in this case because they were yielding negative coefficients, which are not included in the final output. They're omitted from the process. So as an example, let's say we're happy with our edited fit. We're accounting for the major features in the data. We have the concentrations of all the phases in the sample, in this case 42% organic matter, 54% quartz, and some minor components of feldspar and kaolin minerals. Again, if you want to export the data, there are the same approaches down at the bottom. And again, the most data-rich one is this powdR FPS object, which you can save and then load back into the editor again if you like. So you can edit an edited output. And that just about sums up the functionality in this Shiny application. There are various other things that you can tweak in the fitting process, such as this shifting parameter. And this is a way of optimizing the slight shifts on the 2 theta axis of the standards, which can make sure that the peaks are properly aligned. It's quite computationally intensive, so it slows things down a good bit. But by setting this parameter, you are limiting the shifts to a certain maximum 2 theta, which can be useful, and anything larger than that value will be reset to 0, so it doesn't shift at all. Other things you can change are using manual alignment. If you aren't getting good results with the aligning to an internal standard, you can do it manually as well. So have a play and see how they affect the fit, with the ultimate aim of the game is getting as good a fit as possible between the modeled and measured diffraction patterns, which is best inspected using the graphical capabilities of this application. If you have any questions or experience any bugs in this, then please contact me via the contact details of the powdR package.